Welcome, short version of the video on complex square roots. We start with a definition. I take an arbitrary complex number z and then any solution of this equation w squared equals z is called a complex square root of this number z. Usually z is the unknown that we're looking for. Here z is a fixed number. The notation w comes from the German word for root, which is Wurzel. That's why w is here. Was my choice here. So don't be confused. This is not z equals w squared, but w is the variable that we are looking for. So by this definition here, there exist complex roots of -1. The real number -1 viewed as a complex number. And those are simply plus and minus I, because if I square plus or minus I, then of course I get -1. But we are still careful using this notation with the actual square root sign. We're going to talk about that in a minute. Two general remarks. If w is a square root, then of course -w is a square root because it satisfies the same equation. So if w is not a 0, then if I have one root, I automatically have 2. On the other hand, this polynomial here, now again w is the variable, w squared minus z, can have at most 2 roots. Same proof as in the real numbers. And this taken together means if I have a number not equal to 0 and it has a root, it automatically has 2 and exactly 2 roots. The next example is a little more challenging. We're trying to find the square roots of I, the imaginary unit. There's the hard way using the Cartesian form. We're not going into any details here. We're going to talk about that in the next video. But the result is I does indeed have 2 square roots. They are given by plus minus square root 2 over 2 times 1 plus I. You should check for yourself that indeed, if I square these numbers, I end up with the imaginary unit. This is simply to illustrate that using the Cartesian form, it's pretty hard to find square roots. And in comparison, using the polar form is like a fresh summer breeze. And it's no problem at all to find square roots. So here we are using the polar form. We're looking for solutions to the equation w squared equals I, writing w as r times e to the phi I. Now squaring this is easy. I simply have to square the absolute value, r squared. And then here e to the phi I squared is the same as e to the 2 phi I. Because for the complex exponential function we have the same exponential laws as for the real one. And now this needs to be I, so I write I in polar form. Length is 1. The angle with the real axis is 90 degrees or pi over 2. So this is the polar form of I. And now simple looking at this equation, I see one solution at once. I simply take r to be 1. R can't be negative, so -1 is not an option. And 2 phi must be pi over 2. So the first solution for phi is pi over 4. And here we have our first square root of I. Very, very easy. Using Euler's formula, you can transform this into Cartesian form and you end up with the same expression as here. But this, of course, is much more compact. And then, as mentioned before, the negative of this number is another square root. And now, this is very nice, this minus sign gets a geometrical interpretation. I write -1 as e to the pi I, yeah, -1. Is this arrow, length 1 and angle pi with the real axis. And then again, by an exponential law, I can add these angles here, and I end up with this angle. And the geometrical meaning is as follows. If I have found one square root, I simply rotate the arrow by pi, and then if I square this arrow, I end up with 2 pi, which means it gives me the same square as the square of this arrow here. So the minus sign, which is easy to understand algebraically, has a geometrical meaning in polar form. And then generalizing this idea, we end up with this proposition that every complex number in this form, except for 0, of course, trivially, the 0 has 0 as its square root, as its only square root. Each number not equal to 0 has exactly 2 complex square roots, and they are given by taking the square root of the length, the absolute value of the number, length of the arrow. And important, this is the real square root. R is a real number, so here we're taking real square roots and dividing the angle by 2. So e to the phi over 2i. And the second square root is simply the negative, or if you want to write it like that, you add pi to the angle phi over 2. And that's it. Now in the real numbers, this equation has 2 solutions, plus and minus 2. But we define the square root of 4 to be the positive solution of this equation. Now this distinction is impossible in the complex numbers because remember, there are no positive complex numbers. It's impossible to define an order relation on the complex numbers. So we take a different approach. We take the upper half plane, but we take out the negative real axis. This is what I call H minus, the slotted or sliced, I'm not sure which is correct, slotted or sliced upper half plane. I need to take this out to avoid ambiguity between -1 and 1, because then I couldn't decide what the square root of 1 should be. And then I define this symbol to mean the solution of this equation lying in the upper half plane, H minus, the slotted upper half plane. Another way to state this would be to say the argument of the solution is between 0 and pi, including 0, pi not included. In this sense, square root of -1 is e to the pi over 2i, meaning I, the red arrow, and not the dotted red arrow, which would be -i. And in the same sense, here, the square root of I is e to the pi over 4i, and not here this dotted blue arrow. And now this is a proud moment because we have actually understood what the symbol square root of -1 actually means and that it exists in the complex numbers. And we didn't start by the senseless approach by defining this to be I, because that doesn't make any sense. But we defined I using Hamilton's approach and did everything very rigorously, and now we end up with square roots of negative real numbers. That's it. Thanks for watching, and I'll see you soon on this channel if you like.